Hey everyone, this is Mr. Here. This video, we're going to be continuing looking at wave interference. So in this case, I have a picture of the Apple AirPods Pro, and they're really neat because they have this feature, this claim, and it actually really does work, that you've got this ability to cancel sound, unwanted noises. They call this anti-noise canceling. So basically what's going on is somehow you're picking up sounds you don't want, you get rid of them. So you only have sounds that you want going into your ear. Well, how does that work? That's all based on wave interference, which we're looking at today. So let's look at some examples here. So basically what's going on here is that we've got waves that interfere with each other. You can see here two waves are passing right through each other. And what happens is when they pass through each other, they do this really cool thing where they interfere or interact with each other to form this new wave, the black one, that represents the addition of the waves. It has a really, really neat pattern. And that's what we're going to be looking at. So we're going to have two waves. What happens when these two waves meet? They don't have to be exact same size, amplitude, frequency, but when they interact, they interfere with each other. So to simplify things, let's look at just one wave pulse. We can call it a wave pulse. You can look at a crest, or maybe a crest and a trough. Let's see what happens. We use a simulator here. So what's going on here in the simulator is we're going to be looking at two waves that are passing through each other. I'm going to make these waves. Let me just reset things a little bit over here. And I'm going to make them both the same size, both around the same height. Let's make it, oh, let's make actually a little bit larger. And what's going to happen is these waves are going to be passing through each other. So let's take a look at this. And you notice that the waves pass through each other. And when they do that, they don't bounce, actually. It's really cool. Let's look at the large wave. The large wave was here. You can see it continues going through. Similar to the small wave, I'm going to wait for this to reset. When the small wave goes through, it continues moving right through. So the two waves, they pass through each other and they continue moving as if nothing happened. They only interfere for that moment in time. So right now, boom, see if I can catch it. They interfere with each other. And when they interfere with each other, it's only for that little bit. And look what happens. I've got here an amplitude of 2, and the blue wave has an amplitude of 3. Guess what? This wave that results, which is called the resultant wave, has an amplitude of 5. So all you do to figure out the resultant wave, you add up the amplitude of the waves that are interfering. And that gives you this overall large wave. Because the waves are combining to get larger, this is called constructive interference. Well, let's reset this and see what happens if I've got the opposite happening. So what would happen if I made this, instead of a crest, let's make it a trough. There you go, nice trough, -3. So that negative means it's a trough. It's below the rest position. We talked about that in previous videos. So let's see what happens now. The two waves meet, boom, and something interesting happens. Let me slow down the animation a little bit. So they meet, and now take a look. The two waves, here we go. They pass through it, and look what happened. The resultant wave is actually smaller. It's smaller in size because the two waves are on opposite sides. They cancel each other partially. So this is called destructive interference. Let me go back a little bit, and you'll notice when these guys are actually going through each other, what's happening is the two waves, here we go, let me go back a little bit. Oh, the two waves cancel at certain spots and they pass right through each other. Okay, here we go, let's go through this. So here's my one wave, it goes this way, a smaller one, it continues moving, and then we'll wait for this to reset. The larger wave down here also continues to move. They only interfere when they meet. And because the two waves cancel, this is called a destructive interference. Well, let's just take a look at this and see what happens. What would happen if I made the waves the exact opposite height? So one's a +3 amplitude, one's a -3 amplitude. Well, let's see what happens when they meet. Here we go. They're going to go across. Here they go. They're going to meet. What's going to happen? What do you think? Okay, let's take a look. For a second there, the two waves exactly cancel each other. Let me see if I can get it going a little bit here. It's kind of hard. Oh, I had it there. The two waves exactly cancel. And this cancellation point is called a node. You'll see in the diagram, be a little bit better in a bit. So let's do a little bit of a note here, okay? So in my note, let me go back to this. We have this in your workbook. So again, what you want to do is you want to go through this. I'll go through some highlights and you can just copy this down later on. So this is called the principle of superposition. It means basically when two waves interfere, the amplitudes of the two waves are added and you get this resultant wave. Sometimes the waves amplify each other, so it's called constructive interference. The amplitudes add up. And sometimes we've got destructive interference. The two waves cancel each other. What I would like you to do on here, I'd like you to cross off this little bit here. I don't like the wording here. I think it's like super crest or something like that. Get rid of that. And same thing here. The wave that results is called a resultant wave. So you have to modify your note a little bit. The other thing I'd like you to add, if you have crests, I'd like you to add in a positive amplitude. And if you got troughs, I'd like you to add these negative amplitudes. So make sure you fix this note to make it more proper. So here's what we have. I've got two waves. They pass through each other one way. They pass through each other the other way. So they're going opposite directions. They meet, and look at this. The two waves pass through each other, and they continue afterwards like nothing happened. When they meet, they're on this, the amplitudes are both positive. You end up with a larger resultant wave. You just add up the two amplitudes. What if they're both negative? Well, it just becomes more negative. You got negative 10, negative 20 gives me a negative 30. So here we've got a negative 30 resultant wave. Now, what happens when we've got this destructive interference? So again, please add the positives and negatives. So a positive amplitude meets the negative amplitude, and the resultant wave has an amplitude of 15. You simply add the two amplitudes together. Again, they pass through each other like nothing happened. And then sometimes if you've got the exact same size of cancellation, or sorry, amplitude, you've got perfect cancellation, and the temporary perfect cancellation is associated with something we call a node. We didn't lose the energy. The energy is still there in the medium. It's just set up as a, I guess, as elastic potential energy if it's a mechanical wave. So again, the node is very special, but the only way to get that is you've got the same amplitude wave pulses with opposite polarity. We say one's positive and one is negative. Okay, so let's look at some examples now of how to add waves together. So what you do when you're adding these waves together, I've got two waves actually. I've got a one dashed line wave, and it's on top of a solid line wave. Let me show you what these would look like in the simulator over here. So what we'd have, oh, sorry, oh, I don't know if I can do it here. So what we have here, let me make the same frequency. Sorry, give me a moment here. And I'll make this one 256. There you go. So these waves are exactly the same frequency. And if I put them on top of each other, let's overlay the two waves. That's exactly what we're trying to draw here. And what happens is when you've got the two waves, the amplitudes add up. So here I've got two troughs, both have 1 unit. So the resultant wave has 2 units. That's negative. Here you've got 1 unit of amplitude. For both waves, the resultant has 2 units. And you keep going through that. So let me show you what this looks like on this particular wave. So what you do is this. It's going to focus on this part here at the top. So what you're going to have is you're going to have both waves here, both of them at the beginning, and we're going to go section by section here. Both of them have an amplitude of 0, so 0 plus 0 gives me 0. In the next section, they're both around 0.75. So 0.75 plus 0.75 gives me 1.5. Here they're both at 1, so this will be my amplitude here, 2. Here, both of them are at 0.75 again, so you add them up, you get 0.75 plus 0.75 is 1.5. And here we're back at 0. And you'll notice what's happening here is you can smooth this out, and this green thing would be called the resultant wave. And we do the same thing over here for this part. The only difference is you're going to have negative amplitude. So here's negative 0.75, negative 0.75 added together gives you negative 1.5. Negative 1 amplitude, negative 1 amplitude gives you negative 2. And we keep going, and you'll notice the pattern here. And again, I can just continue all the way along, And what we're drawing here is the resultant wave when these two meet together. Okay, so again, it's very similar to the simulation I showed you here, right? So when you do it, it's going to look like this. You keep going across. And again, this is an example of constructive interference where the two wave amplitudes are adding up together. The resultant wave is called the resultant. And the two waves are moving the same way right now, so we say they're in phase. Remember, we talked about phase in an earlier video. Well, let's look at an example now at where the waves are out of phase. So here I've got two waves, again, a solid and a dash, and they're offset by half a wavelength. So we say they're out of phase, or they're shifted by half a wavelength. We don't know which way, but they're just out of phase. And you do the exact same thing here. You basically, to look at the resultant wave, you simply add up the amplitude. So both waves have 0 amplitude here. Both of them have 0.75, but one's positive, one's negative, so they cancel. Positive 1, negative 1 cancels. So look what happens. This wave, and it kind of makes sense, the two waves are exactly opposite each other. So what they're going to do is they're going to exactly cancel. And the resultant wave is going to be this line along here. It's a continuous node. Remember that word node that we used earlier. And this is what it looks like. Oops, let me bring it up a little bit. So this is an example of destructive interference. The two waves are out of phase by half a wavelength. And all of these things along here are my nodes. So these are very, very simple examples, right? Let me just show you a really cool thing. Sometimes what happens is you have the following. Let me see if I can bring it up for you. Where do I have it? Oh, I think I lost it somewhere. Let me just pause for... Here we go, I found it. So what I have here, I've got two waves. I've got a green wave. It's going this way to the right. And I've got a blue wave, and it's going to the left. And sometimes when the waves meet, both troughs come together, like right here, and you end up with a a larger resultant wave. You have constructive interference. Sometimes you've got a crest and a trough, and you've got a node. And it looks like this. Look at the resultant wave, the red one. Doesn't it look like it's standing still? This is called a standing wave, and we'll be looking at this phenomenon later on. Okay, so how about this? What would happen if I had this? What would happen if I had a really, really, really annoying sound? It might be this, like a rattle of a fan. It might be a jet engine, whatever it is. And what I want to do is I want to eliminate this, right? And that's exactly what sound canceling technology does. So sound canceling technology, it's active, does the following. It takes the sound that you don't want and it does one thing. So all of these technologies have a microphone. So what they're going to do is you're going to have a microphone, they detect the sound. And what they do is they make the same sound, they copy it. So let's clone this, okay? But what they do is this, they actually take the sound, and to get rid of it, you have to do something. You have to flip it. So let's flip this. And to keep track, oops, sorry, flip, I'm going to do up and down. And to keep track, let's make one of these just red, just so we can kind of keep track of them. So one of these is red, one of them is blue. So one is the original wave, one is the flip wave. Hey, what would happen if you added these together? When you added the two waves together, you end up with a continuous flat line. And that's exactly what we saw earlier when we looked at this. Destructive interference. So this is exactly when I was talking about the Apple iPod, or AirPods, sorry. What they're doing is they're taking the sound in on this side, they're inverting that annoying sound and playing it back on this side so the two sounds cancel each other. Let me show you a little graphic of how that actually works. Here we go. So again, you have a microphone on the outside. So you pick up the annoying sound. This is this one here. You make a new sound that has the opposite polarity or opposite amplitude. They are played back so the original sound is played is you hear it and you play the new inverted sound at the same time, and look what happens. The two waves exactly cancel. So you want to make sure that you can explain how active sound canceling technology happens. So on your notes, somewhere on this page, I'd like you to jot this down. It's a little note and maybe a little bit of a sketch. You should be able to explain active sound canceling technology. So again, you have a microphone detecting the unwanted sound. The computer creates an inverted wave with the same amplitude and plays it back to destructively interfere the unwanted sound wave. So it's kind of like a neat application, right? You never thought that physics would be involved with your audio listening enjoyment, right? Okay, we're just going to do one more example here, and that's this here. What I have here, this is from your workbook. This is you have two waves, and they're not the same frequency. They're off a little bit. There's a little bit more complicated pattern here, but you still follow the exact same, I guess, technique to determine the resultant wave. So what you do is you add up the results of the individual amplitudes. So I'm going to add up the amplitudes of each wave, the solid and the dashed. So at the beginning, both are 0. So 0 plus 0 gives me 0. Here, this one's at around 0.4. I'm just going to put down the number here. You don't have to. It's just going to help us keep track. This is positive 0.4. This is, I would say, maybe negative 0.7. So you add these together, you end up with negative 0.3. So I'm just adding the two amplitudes together. Again, you don't have to write them down. Then I'll go to the next section. This is at minus 1, and this one looks like it's around minus 0.7. So now we're still at 0.3 if I was to add these together. Let's look at the next section. Now this one over here looks like it's at around, maybe around 0.9, positive 0.9. This here, it looks like it's around maybe 0.7 or something like that. So it looks like we're getting a 0.2 when you add these together. That's my new resultant over here. We're going to keep on going, and I'll go up to maybe around this part here. So 0 here, this is plus 1, so plus 1 and 0 gives me 1. Here I'm going to have, looks like, what is this? Maybe 0.7. This one is around 0.9. You add them together, they're both positive. You end up with 1.6. So we're somewhere up here now. Over here now, look, what do we have? Positive 1. This looks like it's around positive 7, so 1.7 looks like the resultant. So over here. So again, all we're doing, we're adding the resultant, the amplitudes together to get the resultant. Here, this looks like it's around 0.4. And this looks like it's around maybe 0.6-ish, so it gives me 0.1 when I add them together. Almost done, and both of them here are at 0. And then all we'd have to do is we take a pencil and make a smooth line connecting these points. And this smooth line represents what happens when the two waves overlap at that particular spot. Okay, so a second later, obviously this is going to change, but this moment in time, this is exactly what they look like. So you'd have something that looks like this. And at the end of the day, you'd have this yellow line. So you're going to practice a couple of these. You don't have to go all the way through. I'll maybe do like halfway and then do one more, and that should be sufficient practice for you. And so that's it. Again, we'll look at more applications of wave interference in the future. So that's it. Hope you enjoyed the video. Bye.